Sven Lidin, you mentioned that nowadays the chemistry is in the cyberspace. I thought it's far away. I thought that chemistry is just in laboratories.
Well, of course, chemistry is an experimental science, but what has happened over the past few years, it's really a fascinating development. When I was a young chemist, theoreticians would come to us with ideas about how a system behaved. And if their predictions would scan with our experiments, they would be happy. If the two did not agree, we were always sure that the theoreticians were wrong again. Today, when theoreticians come with a prediction that we cannot prove is correct or disprove, well, normally we as experimentalists go back and check our experiments again, because it may just as likely be we who are in the wrong today. This is how far theoretical chemistry has come to become one of the tools, I would say, of experimental science, because the sort of theoretical chemistry that this year's laureates have been laying the foundation for are simulations. They're really numerical experiments that tell us a lot about how chemical systems work. So I would say, to us, theory has become the new experiments.
What happened then? What made the theory to be in this role now?
Definitely the contribution of this year's laureates is central to that, because what they have done is marrying the two worlds of quantum physics and classical physics. Quantum physics will really provide us with all the answers that we could possibly look for. Quantum physics has the wonderful ability to stop time and to expand space, so that we can look at the tiniest detail of a system. And we can look at this during any fraction of time that we choose. The problem is that the demands on computer power are immense, and it's completely impractical to use this for any system of size. Therefore, we have to use classical physics to describe the bulk of the system. And it turned out that to marry these two is no simple matter. It really took a large concerted effort over a number of years to show that it was even possible, which is, of course, what the laureates did.
Quantum physics is a lot about probabilities and statistics. Is this the difficulty?
Yes. Quantum physics is one way of parameterizing the world. Classical mechanics is a completely different way of giving a model for basically the same system. Now, one thing is that you can make the two and compare them, and that works beautifully. The problem is to take one part of a system and describe it in terms of quantum physics, and another part of the chemistry of the system and describe it in terms of classical physics. You then have to find the correct boundaries to put between the two systems, and to use the input from the classical mechanics as boundary conditions for the quantum mechanics, and vice versa. And this means that we can look at systems of, I shouldn't say any size, but we can look at vastly more larger systems and more complicated systems. And this is, of course, what we need in order to understand the systems that chemists are studying today. Huge supramolecular systems, biochemical molecules, large assemblies in material science. And all these disciplines use the theory that was founded by our three laureates. It is really a cross-disciplinary part of chemistry which goes into all the fields and enriches them.
Does it mean that if you don't have the theoretical model, you don't really understand what's going on?
It's always a question of complexity. If you have a simple system, you can get very dependable answers by using just experiment. But experiment and theory go hand in hand. We need to understand why things happen. We need to understand what makes things happen. And as Gunnar Karlström was explaining during his resume of the prize, the real problem is that most chemical methods tell us about what things look like before a reaction and what they look like after reaction. There is a classical picture of this which is given in many textbooks of chemistry, where a chemical reaction is likened to a piece of drama. And if you go in and make the measurements before and after, it's like seeing the actors before Hamlet and all the dead bodies after, and then you wonder what happened in the middle. And actually there is some interesting action there, and this is what theoretical chemistry provides us with, the whole drama.
Yeah, so you want to be in the eye of the storm, so to say.
Absolutely.
I understand. But what are the possible applications of that? What are the benefits besides
I would say
science?
They're not possible. They are there already today. There is not a pharmaceutical company that doesn't have a theory division that works on trying to predict how a molecule will interact with the target in the body. This means that all development of new pharmaceuticals has a background in theory. When you are looking at devising new chemical reactions, when you are trying to create a new hard material or a new material with specific properties, if you want to optimize the electronic properties of material, the magnetic properties of material, you always start out with theory because it saves you so much time in the lab. Now, theory is not perfect. You still have to do the experiment. But the predictions that theory make are becoming so much more powerful these days that we can perhaps save 90% of the experimenting and concentrate on the 10% where we know that the most important results will lie. So we save a lot of money, we save a lot of time, and we save a lot of effort by doing the theoretical homework first. It's like in the old days when everyone told you you have to read the literature. Now everyone will tell you you have to make the calculations.
So now you just sit by the computer instead of being in the lab most of the time.
There is some truth in that, although of course what happens is that we can now turn to ever more complex systems. We can always devise a system that is so complicated from the experimental point of view that theorists still are struggling to keep up with us. But on the other hand, they keep challenging us. If you look at the physics prize for graphene, for example, now the extraordinary properties of graphene were predicted before by theorists. This is why the experimentalists tried to make the material, because it's no simple matter to make it. They tried to measure the properties because they knew that there was something interesting in there, and they succeeded. But it was all thanks to the theory that someone even tried.
So theory and the experiment go ahead.
They really do.
Thank you very much for taking your time.
Thank you.